who will tell us about identifying and exploiting structure in the landscape.
Great, thanks. And a huge thanks to the organizers for making this event happen and giving all of the speakers an opportunity to speak. Today, I'll be talking about a few projects with some great collaborators, Matteo Biaghetti, Andreas Schochner, and Gary Hsu. And in particular, we have hopefully a paper coming out this month, and we'll see. So here's an outline of my talk. As you can tell from the title, the theme of the talk is that data, as it applies to cosmology and string theory, has structure, which we should try to learn and subsequently use. So as an outline for the talk, I'll start by giving some motivation by describing the role of big data in modern cosmology and string phenomenology. Then I'll talk about some techniques, including topological data analysis, more specifically persistent homology, which is a tool for explicitly identifying the shape of a data set. So this constitutes the identify portion of the talk. We'll be applying these techniques to cosmology, in particular, the CMB and large scale structure. Then we'll switch gears and talk about stochastic optimization, in particular genetic algorithms, as a way to try to find interesting string vacua. We'll apply this to flux vacua, and I'll make some remarks on encodings. And so this is the exploit section of the talk, the idea being that a smart search algorithm will learn some structure that it subsequently uses to find optimal states. So cosmology is marching into an era of big data with ongoing and upcoming surveys, making huge numbers of observations, as you can see. And this data promises to greatly aid our understanding of fundamental physics. But extracting physics from these large data sets is complicated by the fact that the data lives in high-dimensional phase space naturally. So if we just take a naive perspective, the phase space of n particles has dimension, which is the number of particles, or it scales with the number of particles, while a generic function on the sphere has dimension that scales with the number of pixels, or if you are doing a spherical harmonic expansion, this goes as L max squared. So our job as theorists is to predict and measure signals in these very high-dimensional spaces to understand or detect new fundamental physics. So we want to examine cosmological correlators in more detail. The lowest order correlation in primordial fluctuations is the power spectrum, or the two-point function in a harmonic space. This is a function of just one momentum due to momentum conservation. And for a Gaussian theory, this is all we have. The power spectrum dictates all higher point correlations, and this represents a huge compression of our data to just the power spectrum, or L max degrees of freedom, for example, if you're living on a sphere. However, Gaussianity is not the end of the story. We know that there is, in general, non-Gaussianity, with the leading non-Gaussianity being the bispectrum, or three-point function in a harmonic space. Again, we have momentum conservation. So if we use scale invariance, which is often a good approximation, we can write a bispectrum down via its size, which is just a number, which we call FNL, NL standing for nonlinear, and its shape, which is now a function of two ratios of momenta. So this gives you a lot of information about the underlying physics, and it's a very discriminative probe of your model. So as Tolstoy famously said, Gaussian fields are all alike in the sense that you can specify them just by the power spectrum, while every non-Gaussian field is non-Gaussian in its own way. So let us then interrogate some of these non-Gaussian fields and see what they can tell us. So some example non-Gaussianities. One very popular phenomenological way of parameterizing non-Gaussianity is with a local ansatz. So here we look at the curvature perturbation, for example. We have a Gaussian part, and we add the square of it. And this induces a non-trivial bispectrum, for example. And it's easy to show that this bispectrum peaks in the so-called squeezed limit, where one of the momenta is very small. And so we have this very squeezed triangle here. This is in part interesting because there is a single field consistency relation, which tells you that for a single field model of inflation, the bispectrum in the squeeze limit must scale with the deviation from scale invariance. And observationally, this is set to be very small, small enough that any foreseeable detection of the bispectrum in the squeeze limit would rule out all single field inflationary models. So as string theorists who think that naturally there should be a lot of perhaps light fields around, this is interesting to think about. There are, of course, other interesting shapes of non-Gaussianity, including equilateral, which scales with, which arises for non-canonical kinetic terms in inflation. Also resonant non-Gaussianity, which you get from an axion monodromy type model of inflation. So non-Gaussianity is an interesting thing to measure. We could learn a lot by detecting it. How do we go about doing this? So currently, the most competitive constraints come from a harmonic space approach where we think about the bispectrum and we fit our data against templates. So there's going to be a different template for a different shape, a different physics that you think might be going on. So we might naturally ask what happens if the template you're using is not correct for the true underlying physics. And then how well you do depends on a normalized inner product between these shapes, which I'm not defining, but you should trust me that it exists. So via this procedure, it's worth noting that some shapes are harder to find simply because they are orthogonal to most other shapes. So for example, the resonant shape that you get from axion monodromy features these wiggles, momentum space, and these prove very difficult features to detect via a template method. Currently, our best bounds come from the CMB via these methods, and the 1 sigma bounds from Planck 2018, I've displayed here, and we see that there's nothing significant. This is just 1 sigma. What we're going to do in this talk is we're going to ask what the real space signature of non-Gaussianity is. And we're going to develop some topological observables via a tool called persistent homology. Okay, so now we've motivated things in cosmology a bit. Let's talk about the role of big data in string theory and string phenomenology. So a lot of the lessons that you need to learn for this subject, we can simply identify within the context of type 2B flux vacua. So GKP showed us a long time ago that if you take type 2B string theory on a Calabi-Yau threefold, that the flux superpotential generically stabilizes the axiodilaton and complex structure moduli. So in a functional sense, what you do is you just take these F flatness conditions and solve them for example, your stabilized VEVs. I'm going to ignore the open string sector for now. This presents us with sufficient richness to have a worthwhile discussion. So you can show that because of flux quantization, in other words, the fluxes that show up in the superpotential are quantized in terms of integers. This is familiar. And tadpole cancellation. So here we have to satisfy Gauss's law in the compact space. And I'm writing L max as kind of in a general way of parameterizing the orientifold charge, that you have a finite number of fluxes for a particular Calabi-Yau. And if you plug in so-called typical numbers, you'll get something like 10 to the 500 critical points. Now, presented with a large data set, such as, with a number like 10 to the 500, we should ask, how easy is it to pick out a particular vacuum from this ensemble? We might be in trouble if the best way to do it is to simply list a large fraction of the solutions, or even a small fraction for that matter. So a hard problem in the precise sense of computational complexity that Fabian was talking about is to ask what is the smallest L max such that you can get a vacuum with certain VEVs and masses in some range. So I'll talk about that in a little more detail in a bit. So the lessons from type 2B flux vacua are fairly general. What we observe is that the space of string compactifications appears large and complex. So if you go to F theory, you can upgrade this 10 to the 500 to 10 to the 272,000 flux choices per geometry, being the current record holder. As well, there are ensembles of geometries with around 10 to the 755 members. So the numbers only get larger. We'd like to ask then if there can be a useful and efficient map of the global structure of the space of compactifications, perhaps utilizing lessons we've learned like mirror symmetry and lessons that we haven't learned yet. Another reason that we're interested in the space of string compactifications from a landscape perspective is that the boundary of the landscape, understanding this is equivalent to the swampland program that so many of us are interested in. And one general lesson from the swampland program has been that there are generically correlations in the landscape, and these can present an obstruction or alternatively a guide to model building. So I think that sufficiently motivates finishing that slide. Now a little bit more on computational complexity. So when we have a large number of vacua, we have to ask how well can we navigate the space. So Fabian gave a nice overview of computational complexity, and also he wrote a nice paper with Jim. So everything we try to do in string phenomenology, computational complexity is making our lives more difficult. So it's difficult to perform the forward map, saying that I have the information I need to specify a vacuum. How do I solve for the vacuum in the sense of stabilizing moduli, solving Diophantine equations perhaps, or computing cohomologies to get the spectrum? So this is computationally complex. It's also computationally complex to perform the so-called inverse map, or find specific vacua. For example, even in toy models, identifying vacua with a sufficiently small cosmological constant has been shown to be difficult by Denef and Douglas in the Busa-Polchinski toy model. So presented with these difficulties, we would surely benefit from some shortcuts and reliable approximations. And this presents a real opportunity to utilize advances in data science and machine learning. So there's been a lot of work on this since the summer of 2017. Fabian's review is the most up-to-date in terms of references, maybe. So in terms of this talk, the relevance of what we'll be doing is we'll be talking about the search for specific vacua using just one technique called genetic algorithms. So now that I've motivated many problems, let's talk about some tools. So this is topological data analysis. I will necessarily be brief, but these textbooks and articles are really great reviews. So what we want to do, we have some data and we want to identify structure in the data. Our most basic notion of shape is topology. Of course, we might hope that restricting to this coarse notion of shape, we would earn some robustness in terms of what we compute. So the core idea of persistent homology is to represent a data set with what's called a filtration, which is just a growing sequence of simplicial complexes. In general, this filtration moving through it corresponds to a coarse graining transformation. So this is natural from a physics perspective. And what we will do throughout this coarse graining is track the creation and destruction of individual topological features. Okay, so we're tracking every P cycle that we find. And I want to just note at the outset that this will be stronger information than the Betti numbers that are familiar to us, which simply count cycles in a data set. So let's look at a specific example. This is the Vietoris-Rips filtration that I'll be drawing for you. So suppose we are given this set of points and we want to understand its shape. Most of you will identify this as a ring or annulus. I believe my mother called it a wreath. So what we will do is draw a ball around each point. And here I'm using nu to represent the radius of the balls. And now if I have two balls that overlap, I'm going to connect them, connect the vertices with an edge. And if I have enough edges to fill in a triangle, I include that triangle. So we see that this is a simplicial complex. And we also see that it's generally not a good idea to only use one coarsening scale. So this is why we're using persistent homology. We increase the coarsening scale, the balls grow, and we observe some more of the global structure perhaps. What we see is that, for example, there are some cycles, like this one right here, but that this cycle will soon be filled in by triangles because it's not very large compared to when it was formed. So we increase the radii of the balls further, and now we observe this strong feature that you probably pointed out to yourself at the very beginning. And this will persist for quite a long time. So persistent homology, there we are. But all good things must come to an end. And in the end, the ball is, the loop is filled in and we just have a ball. So what we just did was we just examined a filtration. And the question is, how do we learn from that process? I'm going to claim without proof that we can compute efficiently the births and deaths of the topological features in the filtration. And so the question is, what do we do with that data? Well, the useful way of visualizing it is with a persistence diagram. A persistence diagram is just a scatter plot of the births and deaths of individual homology generators. So this is part of how persistent homology is refined, is that we can track individual features. We can say, oh, this feature, for example, dies long after it is born, so it must be very robust in the data. And this is the zeroth order intuition, is that long-lived features are real, while short-lived features are noise. I put an asterisk there, so you can ask me why this is just intuition with an asterisk later if you want. So to connect to the Betti numbers throughout the filtration, If you want to know the Betti number for a particular dimension at, for example, time 0.013, you just want to count living cycles. And so graphically, this corresponds to drawing this region and counting cycles over here. So now that we have this tool in hand, we can ask, what are the topological signatures of interesting physics, for example, non-Gaussianity, in cosmological observables? And so now I have two projects to talk about, this older project on the CMB with Gary Xu, as well as some soon to appear work on large scale structure. So for the CMB, how do we give this a topological description? Well, what we can do is we can take, for example, the temperature anisotropy as a Morse function on the sphere, and then compute the sublevel persistence. So this is perhaps familiar to those of you who know Morse theory. So we take some threshold and we look at parts of the domain where the function is below that threshold. So in this context, topological features correspond to cold and hot spots. This is the topological simplification that we're doing, is representing a function via its network of critical points. So what we did in this project is we took some publicly available simulations of the CMB that had a particular non-Gaussianity, local non-Gaussianity, and we computed the persistent homology for these sublevel filtrations. Now, we ended up with persistence diagrams, which we then turned into histograms. So these live in a vector space and we can do nice statistics with them. And what we found is via a toy likelihood analysis, a factor of about 2 of improvement over just the Betti numbers when we use the full persistence information. And I want to warn you that the absolute scale of these numbers is perhaps not representative because we had rather low resolution simulations. So while our current best bounds on non-Gaussianity come from the CMB, we expect that these will soon be beaten by upcoming galaxy surveys. For example, SphereX should get FNL local down to order a few. And part of the reason this is possible is that local non-Gaussianity has a very specific signature called scale-dependent bias, which shows up in the power spectrum. So for example, here we have the halo power spectrum, and it's related to the matter power spectrum overall. And in the presence of local non-Gaussianity, we have this extra term where m is a transfer function that goes as k squared at small k. That means that this term becomes large at small k or at large scales. So there's a feature in the power spectrum, but the power spectrum is just the 2-point function. We might expect that there is higher order information to be used in the data set. And these kinds of higher order correlators are indeed probed by our topological observables. So what we're doing is introducing in this work to soon appear a persistent homology pipeline for detecting local non-Gaussianity and more generally constraining cosmological parameters in large scale structure. So let me tell you briefly about the pipeline. We start with this data set of n-body simulations called EOS, which was run by Matteo. And as I understand, these are the best simulations of large scale structure with local non-Gaussianity on the market. And for these simulations, we compute what's called the alpha filtration. I can define that later if you want, among other filtrations. But the idea is that it's a coarse graining filtration. So we're probing the multi-scale topology of the cosmic web, so to speak. So from our persistence diagrams, we want to get statistics again. In this case, we look at not only persistence images, which are similar to histograms derived from the persistence diagrams, but also topological curves. So you can define these by counting cycles in different regions of the persistence diagram. And this includes the Betti number if we take a difference between two. One technical point is that we subsample our simulations to account for some observational unknowns, like baryon feedback, and some other technical reasons that if you're interested, we can talk about later. So now we have some statistic that we expect to be sensitive to interesting physics. We should ask then, how sensitive is it? So first we perform the step of anomaly detection, which is to say, if you have a statistic that you computed from a simulation that had non-Gaussianity, what is the probability that it could have arisen from a Gaussian initial conditions simulation? As such, we compute this statistic here, which kind of looks like a chi-squared. So here, The D, for example, is of a vector that is your statistic. So this is a kind of standard thing to compute. And what we want to do is we need to account for cosmic variance. We only have access in a given simulation to one realization of a finite number of modes. And so to account for this, we run the pipeline both on our fiducial cosmology, so in this case, Gaussian initial conditions, which form the gray histogram, and also on our test cosmology of FNL equals 10. This is the orange histogram. We can use then the gray histogram to set a cutoff at, for example, 95th percentile of confidence. And we see that, and what I'm showing here as the anomaly is the fraction of the non-Gaussian FNL equals 10 simulations beyond that threshold. And so we see that 30% for these two statistics I'm showing get past that, which we were happy about. So now that you have an anomaly in hand, you want to ask about its physical cause. There could be any number of reasons that your fiducial cosmology is different from your data. So we proceed via a template method. So we start by computing templates, which live in the vector space of the statistic, and they point from the Gaussian statistic to, for example, the non-Gaussian statistic. Now what you expect is for the overlap of data with non-Gaussianity with the template to be more positive than, for example, the mock, which has Gaussian initial conditions. So correspondingly, we compute this other D template, which quantifies how far away you are from the mean of the fiducial cosmology's realizations. And again, we run this both on the fiducial cosmology and on our test cosmology to see how many positive detections we can get. So in the plots I'm showing, we set a threshold at 95%. And we see that for B1, which is actually the Betti number that counts filament loops, 80% of our simulations are getting past that threshold. So we were happy about that as well. Finally, I want to briefly mention that we're thinking about degeneracies. So of course, you have different templates and you want to understand if I use the wrong template, will I accidentally get a false detection of some physics that I think is there, but it's not actually there. So we proceed via a process of template optimality. What we require, we compute this cosine between the data and the template that we're fitting against. And what we require is that this cosine be large. And so here, what I'm plotting is the optimality parameter when we use the correct template for non-Gaussianity. And in the bottom, if we use the wrong template, which in the EOS data set, we only have variation of sigma 8, but we're working on some other cosmologies. And what we observe is that in general, at least for this case, the numbers here are much smaller. And so a conservative cut like 0.8 will get rid of all of these false detections while preserving a lot of the volume. But we're working on a more general search. Great. So a brief summary of the persistent homology section. We see that persistent homology gives us an explicit computation of data shape, and you can use these to introduce new topological observables for cosmology, which appear promising for constraining hard to find patterns like certain non-Gaussian entities. I want to briefly mention also this paper that I had with Gary a while ago, where we use similar techniques to look at collections of flux vacua. Already in the context of simple toy models, you observe topological features which reflect correlations in the data and also the finiteness of the space of vacua, which prevent you from an arbitrary amount of fine tuning. Okay, so now let's switch gears and talk about genetic algorithms. So as you might remember from the beginning of the talk, computational complexity is a real problem in string phenomenology. It affects both the computation of vacua. So for example, taking fluxes and going to low energy properties. And it also affects our search for particular vacua. So in other words, saying I want low energy properties in some range and then finding integer quantized fluxes with tadpole conditions satisfied and so on, that give you that vacuum. So we're going to focus on this latter problem, but there has been some recent nice progress on the further with numerical techniques by this group that I wanted to point out. In general, what we're going to be doing is stochastic optimization, and there are many examples of this, like hill climbing, simulated annealing. We're going to be talking about genetic algorithms, but as Fabian mentioned in the context of reinforcement learning, which is related but not the same, we have some kind of landscape that we want to get to the top of. And so we're going to be oftentimes defining this landscape so that the top has the low energy properties that we want to find. So what is a genetic algorithm? Here are a few of the most recent references, but I know there are more. You can look at this paper for an almost complete list of references in our field. So the genetic algorithm was introduced by Hollins in the 70s, and the core idea is to model the dynamics of the evolution after natural selection. So we start by randomly generating a population of candidate solutions, and we imagine that we have some genetic information about them. So I'm using an alphabet here. So what we do with this population is we compute the fitnesses of the individual members. So in other words, how close to optimal they are, and then we assign resources to the individuals according to their fitness. And these resources determine how often they reproduce. So for example, we choose these two individuals that reproduce here, and we combine the genetic codes of the two parents. So this is sometimes called crossover, and here we end up with a child, ACAD. There's also some probability that the child mutates. So for example, going from ACAD to ACAB down here, we flipped one of the alleles. And you repeat this for just however many generations, and sometimes you are tuning parameters. I'm being very general about how often you mutate and so on, until you have desired results. So let me show you one of the examples that we performed in this paper from last year with Andreas Schochner and Gary Shu. We performed a simple search in this case, but we just wanted to understand the dynamics of the algorithm in practice. So we were taking a symmetric T6. So this is a two modulus space. And we wanted to search for a particular value of the 10-dimensional strength coupling, 0.3, which is not that hard to achieve, but we wanted to understand when GAs work, why they work. And we took a population size of 10,000. So what we observed when we looked at the data is that the evolution roughly divided into 3 phases. Here we're plotting the number of solutions within different neighborhoods of optimality. The first phase is rapid evolution. So some members are just initialized to be sort of lucky, and they rapidly propagate their genetic information to the entire population. In the second phase, we found that there were several optima that were competing, local optima, competing for resources, and so they were sticking around for a long time. Eventually, one of them wins, and the whole population settles into that particular extremum. I just want to point out that when we were trying to understand why GAs work, there is this idea of schema, which gives you some intuition. It says that small chunks of the genetic code give you an outsized positive contribution to the fitness, and you can prove theorems if these schema exist about how often they occur in the population. And so in the 2 extrema case, we found these 2 as schema in the sense that they were kind of flat directions of the fitness. So it seems like, at least for a simple search, this concept manifests itself within the flux landscape. But more generally, we can ask, when should a genetic algorithm or other local search be feasible? You can get some intuition via the fitness distance correlation, which is what it sounds like. It's the correlation between the fitness of a member and the distance to the global optimum. So imagining, just for the sake of argument, that we know the global structure of the landscape, but this is okay just for thinking. Now, a moment's thought will realize that for many cases, the fitness is easy to maximize or minimize, respectively, if the fitness and distances are anti-correlated or correlated. So this just means that local operations are a good guide to global optimization. I just want to briefly point out that the fitness distance correlation depends directly on the choice of encoding you use or representation. So this is what Sven was talking about in the context of some other machine learning tasks. I just want to point out that for the nearest neighbor Ising model, you do have this duality, which is not a self-duality, between, I guess I should draw, for example, you have nearest neighbor spins, or you can also think about there just being a domain wall localized at the domain wall. So you can compute the FDC in both of these frames, and what you find is, of course, in the domain wall frame, it's -1 because the actually in the end, the distance is proportional to the fitness or the energy. And so it's much easier to minimize the potential in full generality in the domain wall frame. Okay, so let me wrap up. What I wanted to convince you was that data, as it manifests itself in modern cosmology and strength phenomenology, has data, which we should try to use. In the first part of the talk, I talked about how we can explicitly compute the structure of this data with tools like persistent homology. And I should mention that I mean explicit as opposed to the implicit representations that neural networks use, which are also very interesting and appeared in Sven and Fabian's talks. And we use this approach of persistent homology to introduce new topological observables for cosmology. In the second part of the talk, I talked a little bit about efficient search strategies, in particular genetic algorithms, and I gave some indication that in the context of flux vacua, genetic algorithms were doing their job, at least on a simple search. But of course, in the paper, we talk about cases where it was not so easy. So I encourage you to read the paper. There's plenty of future work to do for cosmology. We're looking at different kinds of non-Gaussianity, different cosmological observables. I think one of the important takeaways of the paper is that actually we should develop our analytical foothold for persistent random topology, because there's a potential upside that is large, but this is currently something that we don't know that much about. For genetic algorithms and the string landscape in more general, we're looking at higher dimensional moduli spaces and the possibility of testing or validating swampland conjectures. I asked Sven that particular question during his talk because I'm wondering how, this is in a different mode now. I'm wondering how useful machine learning is to discover nice encodings for search algorithms, even though this probably can't be done universally, but how well you can speed things up. And also, I didn't mention that much about reinforcement learning or neural network-based approaches, but I think these, of course, should be combined. Finally, there's an interesting relationship that I didn't mention between search algorithms, encodings, and the dynamics of vacuum selection. For example, thinking about computational complexity as providing a measure for eternal inflation. And that's interesting to think about as well. Thank you.
Thanks, Alex. A very interesting talk. We have time for some questions. Fabian. Fabian, go ahead.
Yeah, thank you very much. Hi, Alex. Thanks for the great talk. I have a question concerning the fact you mentioned about the distance. So there are ways like using gray code to break the Hamming distance in genetic algorithms. Have you thought about using a different encoding? I mean, in this case, there seems to be a good encoding, at least when your data is binary, to precisely avoid this. And so this gives you a good...
So we played around with encodings for the flux vacua. I think we found that doing a binary encoding of the fluxes was better than just taking the integer fluxes as they were. It seems like the encoding is really can be very important when you're trying to find rare states. For example, there's this old paper by Wheeler Rummel where he's looking at encodings in the number partitioning problem and finds that these, if you have a good heuristic, then you can really define your encoding to be kind of perturbations of this heuristic. But of course, finding the encoding in the first place requires a lot of thought. So I think this is a really interesting topic to explore, but so far I don't have any amazing results.
More questions? I'll throw out a slightly strange question. So I think one of the interesting things about the various search algorithms is that they can sometimes suggest physical realizations that you might not have thought of. And so there's the question of whether there's any physical realization of a genetic algorithm. And just, again, to throw out a crazy idea, some sort of a instanton solution where you have a vacuum with different fluxes and the Calabi-Yau swaps pieces or manages to copy the fluxes from part of one vacuum and part of another vacuum. So it'd be an interesting thing to look for.
Yeah, I think that's really fun to think about and pretty interesting. Thanks.
More questions?
I have a question.
Please.
Hey, let me turn on my video. Hey, Alex, really nice talk. Sort of in the spirit of Mike's question, I think you know one of the reasons I'm interested in some of this optimization stuff is connections to the measure and landscape dynamics and whatnot. I learned recently that even in the optimization community, there's something called multiverse optimization that somehow has made it into their community as an alternative to genetic algorithms and simulated annealing and whatnot. I guess my question is, as someone who hasn't played that much with genetic algorithms myself, you know, to what extent, part of the problem with these optimization algorithms for people that aren't optimization experts is that there's too many of them, and it seems like, you know, you can spend 2 days implementing each one, and it's hard to know how much you're going to need to tinker or whether there are rules of thumb ahead of time. I mean, could you comment on, in this T6 case, how much you had to tinker, or whether there's any lessons that you've learned that might be useful for those of us that want to play with some of them?
Yeah, thanks for the question, Jim. So I think in the context of flux vacua, or in the context of certain physical problems in string theory, we end up with boundary conditions or consistency conditions that we want to maintain. So for example, in the search on the symmetric T6, we were satisfying a tadpole constraint, and we set this Lmax parameter to be something, I don't remember what it is right now off the top of my head, but we set it, and it's something that if you're not careful about what your operators are that you're using, then you can very quickly take something that you were calling physical and is no longer physical. So in that context, there was some amount of, I think that some of the things we think about in our community are not the same as what at least I've observed people saying at the very beginning when they talk about genetic algorithms or something. So there's a fair amount of tinkering, but I think that this was a pretty smooth example. Of course, the question is also, you know, if you have an optimization algorithm and it doesn't seem to be working, is the problem that you're not implementing the optimization correctly, or is it just that the optimum, if you don't know the global structure of the data set, doesn't exist? So I think the boundary cases are really challenging, and you know, so far I also don't have a good rule of thumb for picking out a particular optimization algorithm and running with it. So having a favorite is good, but it also limits you.
Right.
Thanks.
I see. A related question, actually, since you're on this slide. So it's interesting you have this little phase where two extrema compete, and I've seen talks by Steve Abel where he, you know, shows the genetic algorithm finding minima of an actual potential, and things can bounce around from one local minimum to another as the ensemble explores the effective potential. So you guys actually saw that in your, I mean, your plot says that you saw that, but you guys actually saw it in your setup?
Yeah, so this was a somewhat general feature. So, you know, I think in most of the searches we did without too much trouble, we observed some phase where there were at least a few optima, but they did, yeah, I think in general, you can observe swapping between the two.
This is part of your guys' paper, this competition.
Yes, I believe so.
I need to read that section. All right, thanks a lot, nice talk.
Thanks.
Okay, thanks. So we'll finish the questions here, and we'll thank